V5 product. So with our V6, 3DCS V6 Variation Analyst, we had a full integration in V5, but the database connection to Innovia V5 just wasn't there the way we wanted it to be. Now in V6, we have the full model stored in the Innovia V6 database. The whole model, whether it's the input of the model, whether it's the FEA data, whether it's the results of the model, the complete variation analysis can all be done within V6. Just a few of the items that we're going to talk about today that we leverage is the V6 live rendering. So you want to do high definition visualization of either a dimensional objective or your variation analysis results. We take advantage of that inside of V6. The FTA, as it was called in V5, is called 3D tolerance and annotation in V6. We still take advantage of that, all linked within the database. Whether that would be on a part or an assembly, we can read that data synchronized to our analysis model. Some things that we're still working on is a link and associativity to the Delmi assembly process planner, whereby we'll be able to synchronize the sequence in which parts get loaded and get assembled in various tooling and fixtures. So we'll take advantage of that. And of course, there's differences in V6 and V5. We had joints and constraints inside of V5 as far as kinematic assemblies, these mechanical connections within V6. We're also leveraging seamlessly as we did in V5. Okay, Dassault has developed a strategy for everything pretty much, and certainly system architecture, assembly design, and machining process, optimization, and reporting inspection is all part of that. What we want to tell you and what we're trying to communicate here is that DCS is there every step of the way to support the DS vision for your PLM implementation, your given product, and whether it would be from a rigid body assembly or a compliant assembly, whether you want to do tolerance optimization, design optimization, whether you're doing point-based assembly inspection or part assembly inspection or feature-based, DCS is providing solutions that provide just a cradle-to-grave type of solution that's right in line with Dassault systems. Some of this is just to give you an idea. If you know 3DCS V5, you know that you can pretty much work with any kind of data. Well, in V6, we're working the same way. Whether you're starting with Class A surface that came from a scan, or whether you just designed that initially right within CATIA, whether you're working with just solid data or maybe edges, points, surfaces, preliminary design is one of the things we really want to take advantage of within 3DCS. We don't want you to have complete definition, product definition, to utilize our tool set. So the benefits of being able to quickly pick primitive elements like points and edges and lines, just single surface entities is what we support. In the assembly structure, the way the product tree is defined is we leverage that. Whether there'll be measurements that are defined within CATIA, we'll leverage that. We talked about the assembly sequence and the product FTA. The idea is that we synchronize, we read this into DCS, we optimize not just tolerances but design and process, and then we don't just produce statistical results, we provide visualization, and we allow the user to really see what the given assembly will look like in that process with live rendering, leveraging the high-D visualization built right into CATIA V6. So how is it different? You know, I got a couple of slides here that's going to talk about the differences, but first of all, we're going to talk about how is it the same. It's the exact same interface. All the DCS functionalities have been ported over. This has been a seamless process for DCS because, and this is going to also give us the ability to continue to develop on 3DCS V5 as well as 3DCS V6 because we don't have to redesign our entire software. Certainly the big part of the tool set is the tie into the database, Novia V6 database versus file-based kind of structure in V5. But as far as the solver, it's identical. As far as the ability to use GD&T, assembly, the same type of assembly data, all that is the same and consistent. Some of the differences, and I'm going to just give you a brief overview of how 3DCS V5 works, is we stored the DCS model in CAT product files, and these might have come from maybe a file server or a Novia V5. But when we wanted to store the model back into a Novia V5, we had to store it as a black box so that the product structure did not get exploded into the V5 database. And we know this wasn't optimal for all of our users, but we supported the workflow. It just wasn't as good as we wanted it to be. Sometimes when we had other files that would come into DCS, like CMM data, coordinate measuring machine data, I should say, FEA data, we're doing a compliant model. These would be maybe stored on a file server that would need to be kind of pulled into the model. And of course, our results were stored in text, HTML types of files that were stored kind of separately from the DCS model. So we kind of had two different, maybe put on a web server. So we have a good system in 3DCS V5, but it really wasn't optimal. So in V6, what do we have different? The big benefit is we're storing everything within the Novia V6 database, whether it's the input of the model or the output of the model. In a moment here, we're going to show you how to load a model, how to access a file right from V6, and you'll see the workflow. But the point is that we don't have to kind of have multiple places for the storage. It's all going within the V6 database. And certainly, don't want to indicate that we don't have any options to say post it on a file server or web server. You still can do this, but the idea is that this is optional to store the data on a file server. It's not required to do that. We want to keep the results right along with the model. So we're going to walk through just with not too many slides, but just a couple, because we want to make sure that we hit all the points. We're going to walk through the steps that we would go through to build a 3DCS model. So this is a very highly recommended step. It's not a requirement. Some people might not be interested in visualizing their parts or their assemblies in high definition visualization. But we want to make a big point of this, that when we produce numbers and results, they certainly are reputable, and we know that we can communicate people to make design decisions. But when we can show them what the vehicle, the product, whether it be an automobile, an aerospace, fit and finish type of condition, or even a consumer electronics or white goods type of product, see, this is what we're going to look like. Well, this is what our product's going to look like. We see a high value to do this. So the first step is really to apply the visualization. You don't have to do this. If it's already done, it's great. We just take advantage of this. You can set all kinds of lighting, and we're really leveraging live rendering of Dassault systems right now, that tool set to do that. The next thing you do is you create gap and flush requirements. Now, certainly DCS solves the problem of gap and flush. It also solves the problems of parts not assembling together, like fitting together, where maybe you don't care about, the customer doesn't care about, they're not going to actually see it. And also there's functional types of things that we look at, like maybe is there too much interference, or maybe some kind of friction that might be coming into play because the parts are fitting together too closely. But a lot of our models are done with where we actually want to see the fit and finish. So what we do is up front, we define measurements, and we define what we call a spec study. And we're going to show you what a spec study is. And a spec study is not a tolerance analysis. It's basically a visualization of a gap or flush condition that can be defined rigid body or deformable inside of CATIA V6, leveraging both 3DCS as well as live rendering. So Elizabeth, can you explain this for us a little bit?
Sure. We have a quick video to show you guys. Let me find it really quick. Okay, so this example, this is the taillight of a car. And let's let it update. There we go. Okay, so what we're looking at here is the visualization right now. As Dave mentioned, this is a gap measure. We're looking at the gap along the trunk and the rear fascia. And we put measures along the edges. And what we're going to do is we want to test out if some measures are at their upper spec limit, some measures are at their lower spec limit, for instance. And this first spec study shows if the measurements are at their lowest measurement. So we can see here the gap along this top is very small. The side looks a little shifted over. And now we can look at this and say, let's render, let's see how it looks in real life. Is that acceptable or is that not acceptable, purely based on looks right now. After this, we can then go in and do a variation analysis on it and get some real numbers. But this is just a quick check before we can even go into it. So this is the opposite case. We set this gap measurement along the edge here at its highest spec limit. So this is all still within our spec, or within what we find acceptable. Again, this is just an example, but you can see here it all looks misaligned, and maybe after viewing this, we decide this was not acceptable. And we can modify that, and with one click, just change the values and see how each different value would look.
So I'm sorry to just bring up real quick. So this is part of this is our perceived quality study, right? So we're doing this early on in the design phase to kind of see how our tolerances are going to affect the appearance of our end product, right?
So that's right. So Ben, like when we do tolerance analysis, especially on fit and finish, one thing we need to do is we have to start with the end in mind. What are we trying to achieve? Now, we can spend a lot of money and we can go out and we can measure what competitors are doing. So we can go on, maybe say a lot in the case of a car, measure a bunch of cars and do a competitive assessment. Or what we can do is maybe pay somebody else to do that and see what a given competitor is doing and say, hey, they hold plus or minus a half, or they hold plus or minus 3/4, they hold plus or minus 1 on their gaps. We got to do the same. Or what we can do is we can take a more engineering approach to this and say, hey, our car has a different fit condition. Our designs are a little bit different than that vehicle that we maybe think is a high-quality vehicle. And let's actually look at what's acceptable to us and what we're comfortable producing the car to. We set this as our objective for our gap and flush through our, not just the exterior, but the interior. Once again, this is just not on cars. It's on airplanes. It's on electronics goods. If it does not look good, there's a perceived quality concern that this is not a good product just because of a look. So up front in the dimensional management process and doing analysis, we want to say, what will this look like to the customer? So it's not a predictive analysis at all. All we're doing is we're taking that gap in flush condition, in this case a gap along the top, and we're saying what would the min look like, what would the max look like, and in this case, you know, the other models we're just looking at whether it's a uniform gap, min or max. Well, what about the waviness or the form to that? In this case, Elizabeth, if you want to just start that again, we actually set, go ahead, explain what we did here.
Sure. So this is one of the gaps here that we set at a min, and here we had a gap measurement that we set at the max of the spec limits. So if we were to allow these parts to be compliant or morph based on these gap measures, this is what we would see.
And this is what is acceptable based on the specification. So up front, we say, hey, what does the gap need to be? What does the flush need to be? What does the the form need to be? What does the parallels need to be? How much waviness can we have in that part? Because these are what our specifications are actually driving us to. So the idea of the spec study, I hope I answered that question for that question that came in. The idea is we want to look at it first and make sure we even have the right target. Because if we meet our targets and it doesn't look good in the end, well then we just wasted our time doing all our analysis. So we start at the beginning.
So you're talking about design and manufacturing targets. You have to have both.
Right. Well, these are basically our design targets. And certainly manufacturing, may or may not be able to meet those targets. So that's a great question. These targets are design targets. Everybody calls them different things. Sometimes they're called DTS or design technical specifications. Other people call them gap plans, specification limits. It's basically on your product, when you ship it to a customer, what will it look like, okay? And that's our objective. Now the manufacturing target should hit that, but how do we know? Well, we build a bunch of cars, you know, we can do it that way, or what we can do is we can actually simulate it using 3DCS to see if we're going to meet that objective. So when we visualize using live rendering, we have it at the front end with a spec study, which is what we're shooting for. And then we have it at the tail end. Did we actually achieve that? Did all the tolerances that go into the part, all the moves, all the processes actually allow us to achieve that? And we can visualize that as well. Okay? All right, I hope we got that one. So when it comes to a DCS model, many of you probably are familiar with this. We have to put in a process. Generally, this is done manually in 3DCS. We say, oh, the fender comes in first. It gets aligned to a fixture. The hood comes down. There's some centering fixture that comes in. And we define functionally how these features align. We call these DCS moves. Well, with our interface to Delmia, we can bring in the sequence that's already defined in the Delmia Assembly Process Planner APS. And that's going to be a huge, huge benefit to reduce on redundancy. We have one place to kind of author sequence. Now, we're going to be limited to that? No. We're going to have the same kind of concept as we do with our tolerancing, which is, hey, you want to bring in your tolerancing, your 3D tolerancing annotation? Sure, bring it in. If you don't have that yet, DCS has its own tolerancing methodology. So the moves can also be automatically created by pulling in the mechanical connections, taking advantage of 3DCS Mechanical, as well as deformable assemblies will be supported through FEA data, directly linking to Simulia FEA data, if it's available, to deform the parts when they're over-constrained. And a lot of parts are over-constrained. And if you're not using 3DCS Compliant Modeler, I think we have a webinar on that maybe we can watch, or we can follow up with some people on that. So once again, the tolerances, we use FTA, that's the V5 term. 3D tolerance and annotation is what we call in the V6. We can extract that and synchronize that data. Once we pull that in, we can run our analysis based on that, and then we can run something called 3D AAO, 3DCS Analyzer and Optimizer, to figure out what the tolerances need to be. And we also have a webinar, I think we did on that within the last month or two, that you can see that. So we can push these values back to CATIA so that once we figure out, hey, can we actually meet our objectives with these tolerances? No, we got to make some changes. Hopefully they're design changes, process changes. They might be tolerance changes we might have to reduce, but hopefully we can increase tolerances. Maybe we have our tolerances too tight. We push them back to kind of ease up the burden on manufacturing.
And that's because, of course, a larger tolerance is easier to make.
It is.
Have to be.
That's right, and theoretically should cost us less. Maybe we would scrap less parts because some tolerance was too tight for some reason. So yeah, definitely that's going to be an advantage to the guys doing the manufacturing. Gives them some options on how they manufacture that part. But we also have the ability to bring in manufacturing data. So we're not using statistical data, but we're actually bringing actual parts in. How we're measuring this, and we have I think a series coming up on QDM before long. We might talk about it at the end, where we have CMM measurement data on the specific points that we want to know, and we want to use that in replace of the statistical value. So we have a lot of options, and these are functionalities that are in DCS, but now we're just taking advantage of those inside of 3DCS V6. Okay, Elizabeth, let's go through another model.
Okay, so this model you can see is an engine block, just a small cut section example. So we have another quick clip to show you. Okay, let's let this load. All right. Okay, so here you can see this is our engine block model, and This is a DCS model that we had originally done in V5 and just imported into V6. So you can see down at the bottom we have this new toolbar, which is consistent with the V6 model. And same tree, everything else looks pretty similar to V5. Here we're adding in measurements. So we're measuring between the top of the piston and the block, top of the block. So again, if you're familiar with V5, it looks the exact same. We're defining it the same way. And here we're saying between plus or minus 5 millimeters, that gap measurement should be. We also have moves. Again, these are pretty similar to what we saw in V5. You can see it highlighted on the screen. This is our mechanical moves. This is a mechanical model, but it's a similar idea. You can see the surfaces that are constraining the part are highlighted, and we have all different moves in this model. So here's it separated out, and then we're going to go ahead and build it, but each tolerance needs to be applied per part. So for instance, here's a piston, and we have imported the FT&A, or 3D tolerancing in V6, you can see, and it shows up here. It's a little small for you guys to see, I think, but it's the exact same thing as we saw in V5. All the tolerances will show up in your DCS model, and you can just import them with one click of the button, and it'll keep track of all the tolerances and apply them to your model. Notice at the bottom we switched to a different toolbar. This is a CATIA toolbar, similar to the fact that we could have different visualization options in our workbench. We can still use that again. The tolerances, this is a GD&T tolerance, where you can change the values the same as V5. Okay, let's go back to our slides here. Okay, I'll hand it back to Dave now.
Okay. So the idea of, you just saw some of the information like the assembly animation, the tolerance deviation. The visualization is very, very important to us, and to be able to run the simulation graphically is critical to us because it helps us see what's actually going to happen in the manufacturing process, which we're simulating here. So in regards to the analysis types, we mentioned the Monte Carlo simulation, sensitivity, whether it's geofactor or AAO. We take advantage of all these types of models, whether it be a mechanical model, a rigid body model, compliant model, take advantage of Simulia, FEA data, and certainly supporting whatever type of approach you want to go to. If you're not into the top-down modeling approach where we try to figure out what the sub-assembly tolerances need to be and work our way down, you can start at the bottom level and build up all your parts and see if you meet your assembly objectives. Supporting multi-stage assemblies and concurrent modeling with 2 or 3 people working at the same time is certainly an objective that is supported within our V6 workflow as well. And of course, the reporting, I think we might get a chance to show that today if we have enough time. I feel like I'm talking too long, so hopefully I didn't cut off Elizabeth's time here. But we have the automated reporting, push-button reporting right within 3DCS V6, as well as an interface to QDM Web so that the results can be shown in our QDM data management system. Okay, let's show them a real demo now.
Okay, so now we're going to do this live. So I apologize if it's a little slow, but we will get through it.
That's just because of GoToWebinar. It refreshes like every quarter of a second or whatnot. So sometimes on live demos, you can see a little bit of a lag. So I'll keep an eye on it to make sure that everything appears properly.
Okay, so this is the V6. I've already logged in, and this is the new V6 interface. So the first thing we're going to do is we've already imported the model from V5 into V6. So what we're going to do is open it. We save our DCS information in what's called a simulation. So you need to specify what type of file it is here first. So I'm going to find a simulation file, which is right here. Okay. So now I'm searching within the database for all simulation files, and I'm going to look for a product that I named tail. It's for an aircraft tail fin. So all I need to do is type it in up here, and it's searching throughout all of our simulation files or 3DCS files for one called tail. So you can see right here I have one. You can notice this icon here. This is the simulation icon. So I just need to open it. So I'm going to right-click and say Open.
So Elizabeth, I think maybe, I don't know if everybody understands V6 online here, but the point is that you're not loading, you have no data on your machine right now. You're basically going into the V6 interface, and I kind of consider it like Google of CAD. I mean, you're searching for a file, you get a list of files that are coming up, and you open that file, pulls it off the web, pulls it off the V6 database onto your local machine right here. So that was kind of phenomenal. You didn't have to say, where did I have this file? You didn't have to say, is it on my this file server, did I store it on my laptop? Everything goes back to the V6 database. And this is the thing I guess I get wound up about, is just because I can't find my files. Where are they at? Now I go to the database, I can search by my name, and I can find it.
And these are all the latest too then. Any updates, changes, every version is still in the system. So you can quickly find it. I only had one version of this one, so you only saw one, but you can definitely manage your files very easily in here. So right now it opens up, and I'm not sure which workbench I'm in now, but I need to get into the DCS workbench so you can see our icons. So all I need to do is go to the compass up here, and we're listed in the south side of the compass. We're under Simulation Apps, and you'll see this DCS Variation Analyst icon up here. So now you can see down at the bottom we have the DCS toolbars. They're the same toolbars as you saw in previous versions if you had V5, but instead of being located along the edges, now they're all just down here. We also have our add-ons, our separate tabs, I guess you could call them, at the bottom. And then we can still have, as the previous video was showing you, measuring, different views, and all of that is just down at the bottom now. Okay? So if we look at this model, this is an aircraft tail fin, for example. We just have one side here to show you just kind of what it looks like. And our goal here was to look at some different measurements, as we said. We wanted to look into some gaps, some flush, and if I show you here, this is one gap measurement we are specifically looking at. This is where two skin panels attach. The skin panels are attaching to the frames at the bottom, and then the frames are coming together. So we want to keep track of this gap measurement, for instance. And you can see here it's measuring from this point to this point, and let's see if you can see the arrow, in that direction. We're also measuring between those same 2 points, but a flush measurement now. So if I turn it, you can see we want to see how the two skin panels step is affected by variation. We're also going to be looking at how this fin moves from its nominal position. So again, we're just looking at this point and how it's moving in this direction. This is just a point on the surface, and it will move with the surface. And the final measurement we're going to look at, these are just, for example, is the clearance between two holes. And if I zoom in here, we'll build it in a bit, but you'll be able to see there's two frames that are coming together, and each has a separate hole on it. So let me zoom in here. So you can see one frame has a slightly smaller hole than the other. And what we're going to be measuring is figuring out what is the largest size pin that can fit through both of these holes.
Now, Elizabeth, one thing I just want to bring out, because it's so cool, is this model we have live rendering on. This model we put materials on, so it even looks more realistic. It kind of gives you the feel of, hey, this is a real thing I'm looking at. So when we work in the environment, the user experience it's greater because, hey, it's exciting. I actually see something that doesn't look like a cartoon. Actually looks like a real part, a real wing.
So let's see, just quickly, we've already applied all the tolerances to this model, so I'm going to deviate. And what this button does is it builds the assembly several times over, and it just keeps repeating. So each of these different movements you see is a different build. You can see how sometimes the skin has different gaps here. Sometimes the skin is, you see the flush, sometimes it's over flush, sometimes it's under flush, which is a big consideration for aerodynamics, for instance. So our gap measures we put in here to keep track of this and to figure out what exact variation we're seeing. Okay, so the way we built this, we now understood what our goals or objectives were. What we wanted to do next was to take it apart and reassemble it the way that it's done for manufacturing. So I'm going to go quickly through this. You can see up here we're building the first center fuselage part, and we're moving the skin to it. Now we're moving these frames to a fixture as well, and moving the skin to the frames, and then the tail. And then we build the two sub-assemblies together by locating these two frames together. Okay, so once we've built it, we then go into each of the parts and apply tolerances. So I'm just going to show you one example. If we move here back to the aft fuselage, notice this is the same idea as in V5, and it's the same tree as you would see in any CATIA model, but we just have additional branches added on. So if we look at this frame, for example, we're going to zoom in on this one. Notice we have the GD&T list, or previously called FT&A in V5, or 3D tolerancing here. And you can see we have surface profile on this feature here. Again, I can open them up. It's the same idea as you've seen in previous versions. We can change the tolerance immediately to see effects, and it's the same idea here. We also have, let me go into each of these teal points you can't really see, but right over here, these are all tooling or fixture points. So we also added DCS tolerances to this. And you can see a profile tolerance to this fixture. We're assuming we have a fixture that this frame is going up to, and these are the tolerances that we added. We also added position here.
Right. And once again, Elizabeth, this is something sometimes we never consider as a big deal, but I didn't have to design that whole fixture, right? I mean, I could simply just simulate that fixture with a simple point, and I might want to change my tooling based on my tolerance analysis. So as opposed to going through the process of figuring out where to hold the part, I can simulate that very quickly in DCS and then drive design, drive tooling, drive process, as opposed to validate design, validate tooling, which are good things to do, but sometimes the analysis doesn't have as much of an impact on the overall quality of the assembly when we do it that way.
Absolutely. Our customers have said that they like that they can design the tooling and the product in parallel now, instead of having to finish the product design before designing the tooling.
Right.
So actually shrinks your product life cycle so that you can design your entire product much faster. The tooling sometimes takes just as long as the product to design.
Sure.
Okay, so once we've added the tolerances, we've reassembled the entire product here. Like I showed you before, and I'm going to reiterate that, the deviation we are seeing, or this change in gap, for instance, or if we zoom in, let me zoom in on your tail fin here. Hopefully you can see a little bit of changes. A little bit slow over the network, but what we're seeing here is the effect of all those tolerances and how we assemble it. Okay, so maybe it's a little laggy.
Let's zoom in really tight. Might see better.
Yeah, you got to get in real close because the system's only picking up snapshots over time. So
you can kind of see that there.
There we go.
Good. Okay. So now we're gonna measure these. We have our measures already put in. We want to see the results. So all I have to do is build it, which applies all of our moves, and then we're going to run an analysis. And I have a couple warnings. I've turned a few tolerances off. And what I'm going to do is I'm going to do 2,000 builds. I'm going to simulate building this assembly 2,000 times and see how many parts are going to be within my gap specs and step specs. I'm just overwriting the old files now. Okay. So here we can see, me zoom in. This is the gap measure, the first one that I showed you. Kind of hard to get both on my screen here, but again, we're looking at this gap measurement. And what we can see here is this tells us that with our 2,000 runs, you can see our spec limits were, I can double check in the measurement, were plus or minus 0.5 from the nominal case. So nominally the gap was 3.5 millimeters. So plus or minus 0.5 from that, we'll accept that as a good part. And you can see here our spec limit lines show up here, and all of our parts fall within that range. We have a whole total range of 0.52 millimeters of variation. So we can then see down at the bottom here each of the tolerances that are affecting that. And if I move this out of the way, let's go this way. You can see all of these numbers correspond to different tolerances that are having effect, and they're all ranked by contributing percentage to this measure in the list down here. If we look at the step now, this is those same 2 points, but we're looking on step. And you can see here, let's see what our, probably can't see these numbers, but relative, the nominal build measurement was nearly 0, and we're saying plus or minus 0.25 millimeters. And you can see on our graph here, about 30% of the time it was either understep or overstep, which would be, again, a problem for aerodynamics, for instance. So we can then look at each of the tolerances that are affecting that and try to minimize those tolerances or figure out what we can do to change that.
Right. And then, of course, Elizabeth, this is one of the times I just want to say, like, okay, maybe the best answer isn't to increase the objective, but go back to that measurement. And let's say I want to just recalculate my statistics, assuming my lower spec limit went to the left a little bit. There you go. And the upper spec limit went that way. Now, we don't recommend that you solve problems just by increasing the specification, but we can get a quick idea where we need to set the spec limits and what kind of CP and CPK levels we'll have based on just quickly changing your objectives to see what's going on. Certainly we want to change the process or the tolerancing or the design, preferably, so that we can kind of keep the same tolerance and same process.
Our other measure was the fin, and seeing how the fin moves relative to its nominal position. Here you can see it has a total variation. You can't read that, but it's 4 millimeters that it's varying total, plus or minus. So again, by the spec limit we defined, we said it could be, looks like about plus or minus 1 millimeter from where it is, and clearly you can see it's not meeting that spec. So again, we can try to improve the model. When you see red, we have room for improvement. So it helps us narrow it down. And our final measurement was the 2 holes, the clearance between them. And 0 means if it's less than 0, that means the holes are crashing. So we have, there's no interference here. And you can see this one's totally in spec. So maybe you could skip over this measure because that one is good. So this just helps you figure out what's going on with your model. So the next part we're going to show you is creating a report. And again, this was a capability in V5 that we liked, and it's still in V6, or it's in V6 now. So we'll keep our results up, and we want to just have a nice looking report, maybe to send to a colleague or a customer, for example. We're going to do the HTML report, and I'm just going to let it run. And what this is doing is it's taking a picture of every move, tolerance, or measure, each of the inputs that we put into the model. It's going to get a better visualization and link everything together so we can quickly see it. So now you can see this HTML report has just popped up on my screen. It has all different kinds of things, and maybe you've seen this with V5, but you can get a summary of all the points in your model, all of the tolerances, how many moves, which is our assembly, and how many measurements. We can go in and see how each of them are applied in what order. So first it applies our tolerances, then we're doing some moves, and then at the bottom you'll see some measures. We can see each of our GD&T tolerances by just clicking on them, and it'll highlight an image of it and then tell you what range was applied and what kind of distribution you're seeing, and a little description based on what you input. Same with tolerances, the same idea. Our moves, we can now see which, you saw me build it and run through the assembly. This looks like it's floating in space because it is. This is our fixture points. So we're moving these objects on the frame to these target points in the fixture, and you can visualize that. And measurements are last part, which you can see in the summary is the same thing. So this groups it per measurement. So here you can see, well, this picture isn't really showing it. This was our gap measure, I think. Maybe I will go to the next one. Nope. Okay. These pictures are all customizable. So this was just, we had saved this earlier for showing something else. But you can change all these pictures to be what you want to see. And this is the gap measurement. So notice this is the same top half of the results that I just showed. And down here, it's showing each of the contributing tolerances. So again, I can click on a tolerance. It'll take me to that page, show me what kind of tolerance, the circular tolerance or position, tells me the range and its distribution. So this is just a nice way to get an overview of what's going on in your model.
What I like about these, too, is when you're doing collaboration with colleagues, it's a really nice way to show what kind of analysis you did. At the bottom there, you can see the analysis settings was one of your options. So if one of your colleagues wants to do the same analysis and see the results, they can go and take a quick look at what you had for your settings so they can produce the same results and go through your analysis in thorough detail if they're using 3DCS. If they don't have 3DCS, they can use this report to see all of the different parts of your analysis and break it down and see how it's all been put together. So they can find out what it is that you did. So when you're explaining a possible solution or you want to point something out that you found in the analysis, they can go and drill down to exactly what it is you were trying to tell them about and show them. And it's all automated. This entire creation process is a push button. So if they suggest a change, you really make the change, push the button, get a new report. You don't spend 2 weeks putting images together, analyzing data, pulling pictures out, or anything of that nature. Exactly.
Okay, so that was all I was going to show you in V6. We're now open for plenty of questions. So if you guys have anything, please feel free to ask.
All right, so we're coming down to 10 minutes to the end of the hour. So we've got a couple minutes here. We're going to stay on the line, just see if there are any more questions. We are going to be sending out a recording of the webinar within 48 hours of our close here. So you should be seeing that email probably later today or early tomorrow morning. I just have to do some quick editing of the video, and I'll be able to send that out. We're also going to be making some of these webinar and presentations available through our partner, DCS Systems, on their website and through our own website. So go ahead and head over to www.3dcs.com to learn more about V6 and other 3DCS solutions. Just want to thank everyone for coming this morning and joining us for our webinar. Please go ahead and head over to 3dcs.com to take a look at our events page in order to see other upcoming webinars that we have planned. We're looking forward to doing another webinar on V6 in 2014 and a series on QDM, Quality Data Management. So please take a look and watch for when those are going to be announced. Thank you so much. I'm going to go ahead and mute the line now and stay on just for a little bit longer to see if there are any questions.